So hello, everybody, and welcome to another Danish Sound Cluster webinar. Today I have some very good guests, like always. But today the topic is feedback and noise cancellation. And as the name so indicates, this is mainly about algorithms that would cancel feedback or cancel noise, or I won't get into, again, many details. The speakers will talk more about it, but it's kind of like an umbrella term for cancellation, everything, whether that's in hearing aids or in headphones or in outdoor noise, but you'll hear more soon. So before I start, I would also like to thank the speakers for being here. Today with us, we have Meng Guo. He's a principal researcher at the MENT. Meng has studied applied mathematics in DTU and then did his PhD with Aalborg University. And he has been working with Oticon and the MENT for quite a long time in feedback system and feedback cancellation and so on. Welcome, Meng. And then we have Simon Doklo. He's a professor at the University of Oldenburg. Simon has his master's degree from electrical engineering and then his PhD from Katholieke Universiteit Leuven, Belgium. And he has been a fellow at the University of, professor at the University of Oldenburg for quite a while, and he has many publications, really interesting and cool work. Welcome, Simon. And then lastly, we have Diego and friends who are talking about a bit of a different, still within the same umbrella topic, but a bit of a different take in the outdoor noise spectrum. And Diego is not here today, but he will join us later because he had some other important stuff to do. So they will go last. And Friends is here joining us from DTU today, and they're going to talk about their work when they were doing their PhD. So I just want to give a few details about this. There is a Q&A only at the end so that we have enough time for people to talk. It's kind of the same format as always, 20 to 25 minutes per person. And then in the end, we take the Q&A. There's a button on the bottom you can press that just says Q&A. You press there and you write your questions. Preferably write them as soon as you have something to ask so that we have enough questions there, and then we go through them one at a time at the end. And then when you get out of the webinar, please remember to reply to this little survey that shows up at the end. It helps us to keep the quality or improve the quality. If you have feedback, we appreciate it. So that's it for me. I'd like to introduce Meng. Welcome, Meng. So if you'd like to share your screen, you're welcome to start.
Thank you. Thanks a lot, Peter, for the introduction. And hello, everyone. I'm very happy to be here, to have this opportunity to give this presentation. And once again, I would like to say thank you to Danish Sound Cluster for the invitation. Today, my topic is acoustic feedback control in hearing aids. And the agenda looks like this. So I will first give a short introduction to the acoustic feedback problem. And then I will go through a few state-of-the-art feedback control methods. Then I will introduce a new approach using spectral timbre modulation. And lastly, I will talk about a little bit our latest research work on the so-called self-learning feedback path database before I summarize the presentation. So let's start with the introduction part. As many of you already know about the acoustic feedback, here are just some applications that you might suffer from this problem. For instance, like public address systems and also hearing aids. Also in the extreme case, like video conferencing. So what happens is that when you have a sound entering a microphone, and then this microphone sound being processed in a way to be present at a loudspeaker. And then the loudspeaker sound somehow goes back to the microphone. You have created this acoustic loop, and this loop is, you can say, the foundation for the acoustic feedback problem. It is a major problem in a hearing aid. It's actually one of the top problems that actually make people not using their hearing aids, even though they have actually paid money for it. Because when you have feedback, it's very inconvenient, and also it destroys a lot of, you can say, the otherwise very nice hearing aid features. The reason for the feedback problem in hearing aids, it's mainly because you can say that the distance between the microphones of the hearing aids, in this case sitting behind the ear, but it could also be even inside the ear canal in a different style of hearing aids. And then the speaker, typically the distance is no more than a few centimeters. So it's they're very close to each other. Also, as the goal of the hearing aid is to make the sound more audible, you will typically need a lot of amplification in the hearing aid. And in some cases, you will actually have this amplification as much as 50 dB. So with this very short distance in between the two and this large amplification, I mean, this is a very, you can say, good condition for feedback to occur. Also, a challenge in the hearing aid application is that the acoustic transfer function from the speaker to the microphones, they are not fixed over time. Whenever, for instance, if you say take off the phone to your ear, you actually change this acoustic transfer function for the sound traveling from the speaker to the microphone, and it happens so fast. It's typically within several tens or hundreds milliseconds. So whenever you have a feedback control system and you have such a change, it has to be able to adapt very quickly. So this is also make it very challenging, to handle this problem for a hearing aid application. Here I just try to model this the whole system in a DSP diagram. So you have an audio system. You have in this case it's a single channel system, which you have only one microphone, but in principle you can have more microphones, and then you have one speaker. And this is typically the case for hearing aid. You have only one speaker, you have the whole processing in the hearing aid. In this case, is modeled by this forward transfer function, and you have this unavoidable, undesired, and unavoidable feedback pass modeled by the feedback pass transfer function H. So this is then you can see the loop that is created in this application, and this problem is actually not new. The existence of the acoustic feedback has been known since 1911. It was actually a Danish professor, Absalon Larsen, who actually accidentally somehow discovered the existence of feedback described in this journal paper in German. And also the feedback, actually effect of feedback is also called Larsen effect because of, the professor Larsen actually discovered that. And so 100 years later, we are still dealing with this problem. And for hearing aid application, this is a major problem. And some of the methods we still use, you can find that in many commercial hearing aids, not only our hearing aids, from Oticon, but from also competitors. Some of the, you can say the methods they're using are more than 60 years old, at least. So to me, this just shows that this is a difficult problem. But luckily, fortunately, there's something we can do about it. And this leads to the next part, that, the state of the art feedback control methods that you can actually find and read and find in the commercial hearing aids. Those are related to signal processing. I mean, ideally, you can somehow say that you can actually totally remove feedback artifacts by using signal processing in an ideal world. This is a bit related to the open loop transfer function and the Nyquist stability criterion. So what it says is that you can calculate the so-called open loop transfer function by multiplying the frequency response of the forward path with the frequency response of the feedback path in a for this single channel system I showed you before. And then there are two conditions of this transfer function has to be fulfilled in order to have an unstable or unstable system. So it's like it says the magnitude of this open loop transfer function has to be equal or bigger than 1, and the phase has to be an integer number of 2 pi. So in human words, it means that whenever the sounds traveling around the loop getting bigger, every loop it goes around, and it's added in phase with the original signal, you will have a instability problem. Therefore, I usually divide, the methods, in two categories. So it's like feed-forward suppression and feedback control, feedback cancellation. So it's like whenever you are dealing with the signal from the microphone to the speaker on the forward path, I put that into the feed-forward suppression category. And typical methods are gain reduction. This can be, this is actually related to this first condition. So in making sure this will not be fulfilled. Then you can have the phase modification part. Also, on the signal in the forward path, this is somehow making sure this second condition will not be fulfilled. Then you can do that in different ways. Gain reduction can be for all frequencies, just and you can basically mute your hearing aids, then you will not have a feedback problem. But that's also, of course, not very interesting because you are also removing the sound from the user. You can then make it, narrow band, so it's like a notch filter. Then there are some disadvantage with that. You can also make it more directional, saying that you only remove sounds from a certain direction. And hopefully, this is the feedback sound direction. And then you can also have this category called feedback cancellation. This is actually working on this guy here. So it's like the feedback part. So ideally, if you can cancel this guy, then you can have all the processing you want in your hearing aid without any, limitations. And this is typically by means of adaptive filter, and that's actually one of the, I believe, in all modern hearing aids in the products you can buy today, you will have this feedback cancellation algorithm. So it looks like this basically. So you have this, you have a kind of adaptive system. Try to model the true acoustic transfer function. So whenever, from an idea situation, if this H hat is equal to the H, then you can create you can say cancellation signal V hat, which is equal to the feedback signal from the real world. Then you can make a perfect cancellation. So in that sense, there is no loop anymore. So you can actually have unlimited gain. But of course, in reality, it's very hard to, as this is also changing over the time, you have to estimate, this acoustic transfer function. So it's like, it's only, I would say on paper, you can make this perfect. So, but actually you can do a lot with this method. And it's probably the most effective method for feedback control, or at least it's somehow, I think, so everyone make use of that. It's actually quite easy to get started. You can have a very simple LMS and it will actually do decent work for a static feedback pass. But the thing gets actually more challenging in a hearing aid application, because you have to actually also be able to handle the changes in the true acoustic transfer function. Also, there's another very challenging part is that actually in this closed loop system, the signal you're going to use for adapting this filter is actually a processed version. So the UN here is actually a processed version of the incoming signal XN. So you can actually show that depends on the signal of XN, you will actually get a biased estimation of the true acoustic transfer function. So this is also something that is that has to be dealt with in a hearing aid. But there are quite a few ways of doing that. And then, as I mentioned before, the other challenge is that this guy has to react very quickly whenever there is a change. Then you run into the limitation of the adaptive algorithm is that you have to handle, the compromise between the convergence and steady state, because you want this H hat to model the H very precisely. By doing that, you can allow a huge amplification in your hearing aid, which is, as in some cases, 50 dB of gain is needed. So meaning that the error between, the true H and your estimate H hat has to be less than 50 dB. Otherwise, you will actually have the first condition of the Nyquist stability criterion will be fulfilled. So you might get into trouble. But for the adaptive algorithm, if you have a very small steady state error, then you will also have a slow convergence, meaning whenever this guy changes over time, saying you put on your phone or you put on your hat, you give someone a hop, the adaptive filter has to actually to react. But if it's not fast enough, you will actually experience feedback. So this is actually another major limitation in using adaptive filter. And this challenge, the compromise between the convergence and the steady state, leads to my next point, is a new approach using a spectral timbre modulation. And so actually this method is something, we proposed this method a few years ago. And the idea is that, during the convergence of the adaptive filter, whenever there's a change, there is a certain period of time the adaptive filter is converging. And during this time, you can say the cancellation performance is not good. You can do several things. You can make a gain reduction, but then you also take the sound away from the user. So this is in my view, this is not a good solution. So what we do instead is that to say, okay, you can then try to use this spectral temporal modulation pattern. So this is, you can say, over time and frequency, you modulate the signal, but you don't modulate it, all the time. And the only one is critical when you can see the feedback can impose a critical situation. So you might have a feedback howling. Imagine if this is the area, then you apply this modulation, spectral temporal modulation, only within, as long as is necessary over time, and only in the frequencies that is necessary. So typically very short. I mean, we talk about tens of milliseconds, and also frequency-wise is maybe 2 kilohertz in the frequency region. And also in this drawing is shown as either the modulation is either 0 or 1, but also you can apply like a soft pattern. So it's like it can be any value between 0 and 1. So it actually sounds, the signal, the output signal sounds modulated a bit, but compared to what you will have otherwise, you can take away the gain, then you can mute, or you can have the feedback howling. I think this is much less annoying, as we can see from this example. So this is from a computer simulations, but we also have like recording and whatever, for our prototypes. But this is just from computer simulation for a illustration. Here you have you can say a perfect situation. So there's either you can say there's no feedback, or is that there's a perfect cancellation. I mean, that's possible in simulation. So you actually, what you see is a clean speech in this case. And then you can have a modern feedback cancellation system. What happens here is that there's a rapid feedback path change, simulating that you are actually moving the phone up to ear, and then here away from the ear. So what happens is that you can say the feedback control system is actually able to stabilize the system after a while. But before it manages to do that, you actually see this as a sound distortion at the output. So this is actually very loud whistling sound. This is very annoying sound, and we want to remove that, of course. By using this spectral temporal modulation, as you can see in this example, I mean, you can see a little bit the modulated signal here and there. But if you listen to that, I mean, it's actually, it will be, you know, very, very easily masked by the signal, by the speech signal in this case itself. So compared to this situation, I mean, this one I think is much less annoying. And this is also what we have seen in, you know, our user test. You know, if you ask people, you know, this is the reference system, and this is the, you know, can say test system. What do you prefer? I mean, it's almost certain that you know, on their answer. Okay, so so that's about this method of using spectral temporal modulation. And I mean, because of time, I don't have, you know, I cannot, I mean, present all our work, but I would hope talk about like a little bit about our latest research work on the so-called self-learning feedback path database. And the idea is that, you know, for a hearing aid, I mean, the feedback path changes are, you can say, whenever there's a change, it can be critical for the feedback situation. And it's actually very user dependent. And also it varies over time. I mean, so what does this mean? I mean, if you look at you know, for a one user and the other, if they have wearing the like identical hearing aids, they will have different feedback paths because of the ears are different, and you know, the acoustic transfer function will be different. But if you look at the, you know, for a particular user, that if I take my phone today or I do that 5 minutes later, you can actually show that this is actually very, for the acoustic transfer function are very similar. They're not identical, but they are very similar. And for different, you know, you can say acoustic movements, for different movements, the variations will be smaller or bigger, but there are some similarities. And this is then, you can say, the basic for this idea is that to say, yeah, but today I haven't seen any, you know, feedback control system actually actively learn from, you know, what it has seen from the past and then make use of that. So this is the basic idea. So it's like if I start from scratch, my hearing aid, I mean, doesn't know anything. But first time I put on my phone to my ear, I might experience a feedback problem. My feedback system, my adaptive filter might converge and stabilize the system. But after that, actually, you can say the hearing aid has the information about this new acoustic situation. And next time, I don't need to start from scratch. I can make use of that. So this is the basic idea. So it's like to learn and store those acoustic transfer functions that it has already been seen before, and then to use them to control the adaptive system, the adaptive filter estimation. If you are interested, I mean, we have some early results in this paper, described in this paper, and you are very welcome to look at it. And also, I will be happy to, you know, receive your inputs because it's still ongoing work. Okay, so that leads to the summary of this presentation. So we had a very short introduction to the acoustic feedback problem. It's a major problem in hearing aids. I talk about some state-of-the-art feedback control methods, feed-forward methods, and also the feedback cancellation. Also the spectral temporal modulation-based feedback control to handling you can say the convergence, to handling the feedback to the convergence of the adaptive filter. And also this latest research work on self-learning feedback class database. Okay, that brings to the end of my talk, and thanks for watching.
Thank you, Meng. Very good. Just a short question. You're saying that it's very user dependent, but I remember that in the fitting software, when you're fitting a hearing aid, you can do a measurement of the feedback path, right? And you use that. Is that related with any of this, or is it something else that you're talking about?
I would say, we are still in a very early stage. What you say makes very good sense. I mean, you can, during the fitting, many manufacturers actually recommend you, even force you to make a measurement of the acoustic situation. But this is just a static measurement, you can say stationary measurement, that you are sitting still with nothing around your ear. So what we do then, you can say, is then, so what they do in the fitting software is that based on this measurement, they will somehow setting up their feedback cancellation, feedback control system. What we thought this database is that, I mean, in principle, you don't need to do this measurement. It can be done automatically. You put on the ear and it just learns. This will be one acoustic situation. So, nothing around the ear. And the first time you go, you put on your phone, it can see, now it changes. I learned this is my second one. I put on a hat, a kind of cowboy hat. This is my third situation. So I think you can say it's an extension of this basic measurement that you do in a fitting situation. So it's like, and also, I mean, this will be, I mean, what I mean is different is that it's like if one person, I mean, one might not experience this at all because, I mean, the user can stream the phone call. So you actually never put on the phone. But then maybe this person, is a professional driver. I mean, sitting a lot in a car, then you have a window very close by. So that will be then the most critical situation for feedback. So there are a lot of, I think,
absolutely. Perfect. Thanks a lot. All right, then we go to Simon. Welcome, Simon. Is it Simon or Simon?
You can say whatever you want.
Okay.
Simon.
Okay. So I like the American way. So Simon, go ahead. And
okay,
the stage is yours.
Screen?
Yes, we can.
Okay. Thanks a lot also for inviting me to give a talk. Thanks, Pedro, and also the Danish Sound Cluster. So my talk will be a little bit have overlap also with Meng's talk. I will also talk about feedback cancellation. But in addition, I would also talk about other applications that can be used for hearables, namely sound equalization, namely acoustic transparency, some active noise control, and maybe if time permits, also own voice pickup using the internal microphone of such a device. So we're talking about such kind of devices, hearables, not only for, let's say, hearing impaired persons, but also for normal hearing persons. And the long-term objective of such devices would be, of course, to have acoustically transparent speech communication using these earpieces. And the device we're using here in our research is actually a research prototype that has multiple microphones and multiple receivers or multiple loudspeakers. And the aim of this research project is to develop and also evaluate, of course, individualized algorithms, both for sound pressure equalization at the eardrum, leading to so-called acoustic transparency. Secondly, also acoustic feedback cancellation, as already mentioned, active noise control, I will also talk about. And as mentioned, as time permits, I will also talk about this own voice extraction using the in-ear microphone. To give a bit an idea about the device we're talking about and we're using here, it's a specific device, but it's also a research prototype device. It's a one-size-fits-all design. We call this the earpiece. The special thing about it, I hope you can see my pointer, is that it has multiple microphones inside here, this vent. It also has multiple receivers or loudspeakers, and it also has even two microphones in the concha. Now, many people would ask, do we really need all these microphones and loudspeakers? The answer is no. But as I mentioned, we use this for research to figure out how many microphones, how many loudspeakers can we use, how can we use all of these devices for a joint combination of all these objectives. And also we're figuring out where should all these microphones and loudspeakers be in the device. There's actually two versions we have available, one which is vented and one which is completely closed. And if people would like what I'm talking about and they would even like to have such a device, maybe after the talk, it's actually, you can purchase it at Hearing Center of Oldenburg, which was, this device was made in combination with a small SME. Okay, if we go to the main objectives of the algorithms for this device, as I mentioned, it has multiple loudspeakers, multiple microphones. If you look at acoustically transparent sound presentation or sound equalization, the main goal is actually to enable hearing comparable to the open ear while wearing this device. And that means if you look at this from the algorithmic point of view, it boils down to equalization, either using the single loudspeaker or using the multiple loudspeakers, and then designing an equalization filter. Secondly, as already mentioned, we would also like to individualize the solutions for this device, to have individualized algorithms, because each ear is, of course, quite individual. And although I will not talk about too much in this talk, we're also collaborating with a professor who is a specialist in individualized electroacoustic models, and we're trying to integrate these models into the design of the filters, both for equalization as well as for active noise control. The third thing, especially, of course, if there is a large coupling between the loudspeakers and the microphones, as Meng just talked about, we need acoustic feedback cancellation. And there, in addition to adaptive filters, as Meng talked about, we tried here another approach where we use spatial filters to actually steer a robust null towards one of the loudspeakers, also aiming at canceling then the feedback contribution in the microphones. And then last but not least, of course, it's a hearing device, so we also integrate this with hearing support, the typical support, which is amplification and dynamic range compression, but also active noise and occlusion control. So let's go to the first topic, or the first kind of algorithms I wanted to talk about, which is sound equalization, or aiming at acoustically transparent sound presentation. And the main goal is here to actually, while wearing the device, to achieve a sound pressure at the aided ear, means when the device is active, that is equivalent to the sound pressure at the open ear, so when not wearing the device. And what I will mainly talk about here is algorithms that aim at physical equivalence, but of course, what's really desired is, of course, only the perceptual equivalence. What this boils down to, if we look at the scheme here, is that if we have one of these microphones, we filter it. I hope you see my pointer here. I don't have this red button, but I hope you can see it at least. We filter one of these microphones and then have a multi-channel filter. If we have multiple loudspeakers, that will generate some sound, and hopefully this sound, together with the sound that is leaking through the device, will be equivalent to the sound of the open ear. So mathematically, if you write this down, it just means that the superposition of this equalized and processed signal played by the device, plus the signal leaking through the device, that's actually this leakage component, should match the open ear transfer function, of course also processed using the hearing device processing in this forward path. So that's basically how this filter A of Q, this equalization filter, should and can be designed, both for single loudspeaker as well as for multiple loudspeaker problems. And when optimizing this, what we actually did is just go time domain, have a least squares design for this filter, and actually a robust design, because as I mentioned, each ear is different. Also, when you put in this device multiple times, we will have different effects actually by putting it in multiple times. So we aim at actually a robust design procedure. And so when formulating this, this problem in the time domain that was on the previous slide, we actually can write this here in this least squares problem. We have a couple of small tricks which are quite important. For example, if there is a processing delay in the device, it may typically lead to comb filtering effects. And to counteract these comb filtering effects, we have this frequency-dependent regularization term. Secondly, to account for non-minimum phase components of the transfer functions, we also have a so-called group delay compensation, which is used in the delay of the filters. And thirdly, as I mentioned, to make the design more robust, we actually include multiple measurements of these transfer functions into the design. If you now look at the simulation results, so this was really for this device at some processing parameters where there was actually a relatively large delay, which we included here in order to check if we could also get rid or counteract the comb filtering effects at least a bit. And for certain gains, namely for 0, 10, and 20 dB, what is plotted here on these two figures in the left is actually the equalization performance when using only one loudspeaker, and here is the equalization performance when using multiple, in this case, two loudspeakers. And what is shown here is in the dashed line is actually the occluded response, so when the device would be on, but there's no processing. Then in the solid black line is actually the desired response. So that means the open ear response times the gain of the device. And then in the gray line is actually the aided response. That means after processing. And of course, the black line the gray line should be as close as possible to the black line. Then we would have achieved exactly the desired response. And what can be seen here overall is that for most gains and also for most frequencies, both using one loudspeaker as well as using two loudspeakers, even when having a processing delay of about 6 milliseconds, you can get a relatively good performance, although there are also some comb filtering effects which are visible. But if one would not have included this regularization, there would be really huge comb filtering effects. So in total, I would say using this technique, which is a unified strategy, a unified least squares design for multiple loudspeakers to design equalization filters, we can get quite a good performance using this device. At the end, we'll also have a slide where we did some perceptual experiments, and there we can also show that actually, even compared to also commercial devices with a smaller processing latency, it actually achieves quite good results, actually, very good results. The second topic I wanted to talk about is acoustic feedback cancellation, and actually there already Meng gave a very good introduction, so I don't have to state the basic problem. The figures look also very similar, but I will still say something new here. So as Meng also mentioned, there's actually two, or maybe I would say three kind of approaches to cancel or suppress feedback. First of all, feed-forward suppression, which Meng also mentioned, would lead to distortion. Adaptive feedback cancellation, where the aim is that this filter, this adaptive filter, matches as well as possible this feedback path. And then I would say as a third approach, we can also have spatial filtering approaches, which then require multiple microphones. One could see this also as a feed-forward suppression approach, where one has multiple microphones, but I would still like to point this out as a kind of a third approach, because it leads to quite different algorithms. And in this third approach, using spatial filters, the aim is to design a spatial filter, we can call it beamformer, which actually puts a zero, should be a robust zero, in the direction of the loudspeaker and of the receiver generating the feedback. If I can null out this direction, while still keeping, of course, the desired sounds intact, then one has also designed a good feedback canceling system. What I would now like to talk about is one adaptive feedback cancellation approach we also designed, maybe as a competitor to what Meng talked about, and then also one approach where we really exploited the fact that we have multiple loudspeakers and multiple microphones in this device present. So, as Meng also said, in adaptive feedback cancellation, there are quite some issues. it's not as easy. It's a bit tricky actually to get this working for adaptive feedback cancellation. It's not as easy as, for example, for the acoustic echo cancellation. And there's actually, I would say, if you just apply the LMS or NLMS algorithm, there's a bias due to the correlation between the loudspeaker signal and the incoming signal, this incoming signal X of K. However, what is sometimes not really reported in papers, if we use this kind of algorithm and some howling occurs, for example, exactly if we move a telephone close to the ear, then actually this LMS algorithm, although there is bias, it actually has a fast reconvergence from this howling. Second kind of algorithms, a bit more complicated, but also actually used, I would say, in practice, is this prediction error methods, LMS algorithms, which actually pre-whiten the signals, pre-whiten the microphone and the loudspeaker signals using a pre-whitening filter here, A of K, in order to actually have no bias and to have a very low misalignment. So the scheme looks a bit more complicated. Basically, it's not that complex. Basically, there's just a pre-whitening with this filter A of K and then the same kind of adaptive filtering. And the advantage of these kind of methods is that they have a reduced bias. But however, and also typically not reported in many papers, is that if there is some howling, they have a could have a very slow reconvergence from these howling periods. So a couple of years ago, we actually came up with a hybrid system that just combines both of these updates and actually merges the advantages of both of the techniques, of the LMS technique, which has a fast reconvergence from howling, and this prediction error method, which has a reduced bias or a very low misalignment. And the idea was actually to have some stability detector based on a soft clipper that actually quickly detects if there is howling or not. And if there is howling, actually will go to LMS, which has a very fast reconvergence. If there is no howling, it will actually use the typical prediction error method, which yields a low misalignment. So merging the advantages of both methods. These are the equations, maybe not that important for this presentation. If you look a bit at the simulation results, what is shown here is the added stable gain and the misalignment. So added stable gain, the higher, I would say, the better. That means you can get more gain into the system. Misalignment, of course, in simulation, we can check what is the error between the identified impulse response and the true impulse response. So the lower, the better. And what is shown here is in the blue line is this prediction error method, which has a low misalignment. And then this hybrid system, this HNLMS for 3 different step sizes, which is a switched combination between LMS and prediction error methods. And what you can clearly see here is for at least this simulation, of course, there's other simulations, and also for a very fast feedback path change in the middle of the simulation, that this hybrid LMS algorithm converges much faster than this prediction error method, while maintaining, of course, a similarly low misalignment. Okay, so that's one part of acoustic feedback cancellation methods on adaptive filters. As mentioned in our device, this so-called earpiece, we have the possibility to also use multiple microphones to design a beamformer, to design a spatial filter in order to cancel feedback. So in this second class of approaches, this is the basic processing scheme. We have our loudspeaker, we have multiple microphones, and now we process the microphones using this beamformer, using this spatial filter W, in order to steer a null towards this loudspeaker. Mathematically speaking, this can be done if we would have an estimate or a measurement of this feedback path by designing the beamformer such that W transpose times H is 0. There's a very easy solution, namely W is 0. That, of course, it means feedback is gone, but everything is gone. That's, of course, not what we want. We also want to preserve the incoming signal. And that can be shown, we can write this as follows, that W transpose times the relative transfer functions for different directions for the incoming source can just be a delayed version, if you will. That's even allowed. So this, these 2 conditions need to be satisfied. And actually, we've come up with different design procedures to design then such beamformers. And I will not go into details for all these procedures, but there's actually 2 classes of procedures. One class of procedures, I would say, easy ones, least squares-based procedures, which minimize the residual feedback power in the left column. And in the right column, algorithms that say, okay, for feedback cancellation, my aim is to maximize the gain. So let's also design these filters such that they maximize this maximum stable gain. And they lead to a bit more tricky problems, so-called min-max optimization problems. And then on the one hand, we can have a hard constraint saying, oh, for all directions that I have in my, my filter design problem, the desired signal, so the incoming source, should be really kept. There should be no distortion. Or I can have a little bit more of a soft constraint where I say a little bit of distortion is maybe allowed. If you now look at the simulation results for this specific design device, and what we showed here is the added stable gain, yeah, for these different design solutions, where LS stands for least square solutions, either with 2 microphones, namely the 2 microphones in the vent, or with 3 microphones, with an additional microphone also in the concha that we use. And MM stands for this min-max optimization problems. What you can see here, and it's actually also what we did is try this out for different reinsertions in order to check if it's also robust against different reinsertions. And we also checked what happens for the incoming signal from different directions. And what you can see is that we can actually have a very robust and very high added stable gain in this device, because the relative transfer functions of these 2 microphones in this vent are actually quite stable, even for different reinsertions and also for different directions of the source. And at first it sounds maybe surprising and unbelievable, but we can get up to 50 dB of robust added stable gain in these kind of devices. Of course, because of the specific design and the specific construction with these 2 loudspeakers, through 2 microphones in the vent. And what can also be shown is that for different directions, the PESC value, if we compare it to the unprocessed version, that we can actually get very high PESC values, so we don't really distort the signal. The incoming signal also really sounds quite good. This was also then shown in a perceptual listening experiment, where we tried out both this acoustic sound pressure equalization as well as feedback cancellation in our research device. It's this column here, or this result here, where we compared it to different hearing assisted devices and also some simple true wireless headphones. And we checked how good the quality was actually, without in this experiment giving the reference signal of the open ear. And what you can see here in this PESC-like, in this Meshra-like experiment, is that for the occluded ear, the results are quite poor, obviously. For the open ear, it's quite good, not perfect, because just people rated what they heard. And then for all the devices, you can see that for our device, as well as one of the hearing assisted devices, I will not say which company this was, actually the performance was actually quite good of the sound pressure equalization in combination with our feedback cancellation. If you want to know more, there's a journal paper describing more extensively these subjective listening experiments. The last topic I still wanted to talk about is active noise control using this device. And as probably many people in the audience here know, the aim of active noise control is to play back some anti-noise by one or multiple loudspeakers, aiming at generating a zone of quiet at a certain position. And in our application, I would say that certain position should be the eardrum. Yeah, that's basically where we want to create also robust zone of quiet. In general, I would say there's a classification of this ANC or active noise control approaches into feed-forward approaches, which typically filter a reference signal on the outside of this device, and feedback approaches, which just filter the error signal, typically inside the device. There's also combinations of these, but I will not touch upon these combined approaches. Actually, it can be shown that using feedback ANC approaches, you typically get a better performance, so a higher reduction of the noise when you also have more diffuse kind of noise not coming from a certain direction. So we focused on these kind of approaches, and we basically wanted to check what is a multi-loudspeaker approach in the feedback configuration that will yield a low sound pressure at the ear. And in many approaches, they will just actually design the filters such that they yield a low sound pressure at the error microphone, at this position where R of N is, but not at the eardrum. So what we came up with is an extension of so-called virtual sensing approaches using multiple loudspeakers, aiming at minimizing the sound pressure level here at the eardrum. So basically in this block scheme, what is shown here, we have the incoming microphone signal, R of N, and basically it's here filtered by this filter W, yielding multiple loudspeaker signals that then should create an anti-noise, which would cancel the noise D of N arriving at the eardrum. Where S of Z is the acoustic pad between the receivers of the loudspeakers and the eardrum, and B R of Z is the acoustic pad between the loudspeakers and the error microphone. So supposing we have some good estimates both of BR or S, which can be done either by measurements or by adaptive filters or by also electroacoustic models, which we're working on, it can be shown that the sound pressure, so the power spectral density of the sound pressure at the eardrum, can be written as follows here with cross power spectral densities between D and R, also the filters here, and also all these acoustic transfer functions which are involved. Looks a bit maybe complicated. If you then have an assumption, which we did not come up with, so-called virtual microphone arrangement, it basically assumes, although it's not completely true, of course, that D is equal to R. Yeah, so only for the design of the filter is it assumed that the sound at the error microphone is the same as the noise arriving at the eardrum. If we then plug this in and assume that we also have cancelled this pad here, this feedback pad, then the expression becomes more simpler. Yeah, actually relatively simple. Although it should be realized, this is still a non-convex optimization problem. So what then our postdoc at that time did is apply his previous knowledge in optimizing this problem, and we turned this non-convex problem into, I wouldn't say an equivalent, an approximate convex optimization problem. Instead of minimizing this term, or let's say minimizing 1 divided this term, we just maximize this term, this denominator. Also subject to some stability constraint, because also in feedback control, of course, one needs to make sure that the filters are stable, that they don't amplify too much, and that also the filters themselves have a limited norm in order not to overdrive the loudspeakers. So by this approach, let's now look at some simulation results where we compared two kinds of things. Let's say classic approaches, where classic here means minimum variance control at the error microphone, not at the eardrum. Yeah, and this is a result for a single loudspeaker and this classical design. And what is shown here is in blue is the attenuation, so the active noise control performance. If you then use our approach, this virtual microphone approach, with a single loudspeaker, we can see that we also have a larger attenuation bandwidth using this virtual microphone approach. And then by using multiple microphones, multiple loudspeakers, of course, in order to design these filters, you can even see that we can gain, especially at the low frequencies, even a better attenuation. So these virtual sensing approaches have quite some benefits, I would say, for designing and for creating the zone of quiet at the eardrum. And also there's some benefit of using multiple loudspeakers. So the last topic I will skip, yeah. And what we're working on at this moment, so in the future, we're also, all these approaches now have been designed, I would say, just for having acoustic transparency for all kinds of scenes, also active noise control for canceling all kinds of noises. But you might also imagine that it's worthwhile to only cancel some sources, some directions. So we're working now also on direction selective acoustic transparency and active noise control, which can be steered by a computational acoustic scene analysis, so knowing where some sources are. I would say, as everybody's doing now, of course, also looking at deep learning-based approaches, deep learning-based active noise control, where there could be some advantage because you actually can I would say, almost predict the future. And of course, latency is always a big issue in active noise control. So that's also an area we will be going into. Then a topic I didn't have time to talk about, but you can imagine if you have such a device with an in-ear microphone. In the in-ear microphone, if you speak yourself, you have actually a very low noise signal. It's only your own voice, but it's very dense. So we're also working on own voice extraction, again, using DNN-based algorithms that do combined bandwidth extension, noise reduction, and equalization, where in the last year, we've come up with some methods that also model this relative transfer function between the outer and the inner microphone using speech-dependent models. And all of this, I mean, even at university, we want to really implement this. Of course, we'll implement this also in a low latency processor as a cooperation with the Fraunhofer Institute here in Oldenburg. I think I've gone over my time by maybe 1 or 2 minutes. Sorry for this, but thanks for your attention, and I'm open, of course, for questions.
Fantastic. Thanks, Simon. Really exciting work. All right, I won't ask any questions because we will have plenty of questions later. But if you can stop sharing your screen, then we can say hello to the remaining speakers, which is Franz and Diego, who's here with us now. Welcome, Diego. So who's going first?
Hey.
Are you going first, Franz?
Yeah, I'll just introduce us, then Diego's gonna go first, and then we switch in the middle.
Exactly.
So,
you guys do your thing. Cheers.
Diego and I, we're gonna show some work of our PhD, which we largely wrote together, or we worked on this project together. Diego is now at Jabra, so we use this opportunity to team up again and talk about this together. And this will be a good turning jump off point of what Simon said. So we're gonna actually also talk about active noise control, but in completely feed forward. So no feedback here, but we go large scale now. Now we don't want to cancel at a single point, but at many. And I'll let you start, Diego.
Cool. Can you hear me? Can you hear me? Yeah. Okay.
Yeah.
Cool. Yeah. Hi guys. So yeah, I'm very happy to be here. And yeah, as Franz said, this is something we did in our PhDs, and we used to do it together. So why not? Once more? Large scale outdoor. So we all know the the cultural value of concerts, right, in cities, and that is like super cool to have in large cities and events like that, like the one we see in this picture. But it's also a problem for neighbors, and there are more and more neighbors that they were complaining about these kind of issues, and municipalities they were aware of. And we had the opportunity to participate in such a project where we could maybe help alleviate this issue. And also because, I mean, it's also the World Health Organization is aware of it, and it's rated as the second largest health threat is noise pollution nowadays. So it's quite important to have both cultural events that they bring value to the city, but also to have good rest and good peace in your city as well. So yeah, I will just go to the next one. So what we knew, or what we know still, is that music is basically a low frequency problem, or concerts are a low frequency problem, and that's because sound propagates unevenly over the frequency spectrum, and higher frequencies, they tend to attenuate quite fast compared to low frequencies. So at the bottom, we can see a couple of examples of what we mean with this. So to the left, we can see the attenuation coefficient of sound due to air, and it's only at high frequencies where we can see certain attenuation, which is actually quite low, but drastically lower at low frequencies. And the same happens with the passive absorption or passive elements, such as glazing windows or walls, right? That we can attenuate quite a lot the high frequencies of traffic noise, but still the low frequencies are going to be transmitted easier. So that means that we have to tackle the low frequency problem, and yeah, just go to the next one. That's fine. And the nice thing is that, okay, we know that low frequencies can be, let's say, controlled actively easier than higher frequencies. So then we have some kind of area there or gap that we could investigate. And if we take the same problem of the introduction and we put in some kind of diagram, we could look at it in this slide that we have right now. So we have here is the primary source at the left, and that's basically the concert sound system. And then we have the audience area where we want to have loud and nice sound, right? And then we have some array of control loudspeakers, which we will tweak with our magic, you could say, such that we keep the sound loud at the audience area and how it should be. But then we reduce the impact of these primary sources in the control area, which in the case that we have here is the neighboring area where some buildings are placed. And to do that, what we apply is sample control, and basically what we can see here is that we have to find a set of filters, W, and these filters they will shape how the sound field is in both bright zone and dark zone relative to the secondary sources, such that the sum of both the primary source sound field and the secondary sources sound fields basically fit some kind of optimization or yeah, we could say objective function that we will define later. Yeah, so we can go to the next one. Yes, just to see a little bit how it is. For maybe most of you guys is quite obvious, but in the end, what we have is some line array of subwoofers. So because it's the low frequencies, in the end we focus on canceling the sound field of the subwoofers of the PA system. It will create some wavefront. In this case, it's free field, so it would be a wavefront. It will be way more complex when we go to actual outdoor concerts. But well, this is just an illustration. And we can see in blue that would be the bright zone, or where the audience area will stand up, and then we have the dark zone or control area where the neighbors, or yeah, where we want to basically reduce the annoyance. And then if we see at the sound field created by the control sources, then it will be a sound field that it already looks more or less as the one that we have in the dark zone from the primary sources, but in antiphase. And then we will try to also optimize such that the radiation to the back. So that would be either because the sources are already directive, or because we combine multiple sources to have this directivity, then it doesn't radiate so much to the back. So the audience area sound is not intact, but sufficiently intact. And then the final sound field would look like something like that, like what we see right now. Right? So we have still a good sound field or good sound quality in the audience area, while the sound field in the control zone is attenuated. Yes. So the main three questions of this talk are: can sound be controlled at large scales? And when we talk about large scales, we talk about hundreds of meters of distance, both in propagation and also in control and size of the areas that we want to control. At the same time, can it be made feasible in practice? Because if we only pay attention to the figure at the bottom where we have this diagram, then we have to measure this, you could say, transfer function between every source and every point that we want to control, right? And that probably we can anticipate already that's quite difficult to do in such large scale. And one of the reasons also is because what is the influence of weather variations, right? Imagine that we are even able to measure all these positions, then weather will change, and okay, we have to retune the system again, and it's quite cumbersome to do. Yeah. So as anticipated before, there is an objective function for this pressure matching or sample controlled approach, which we can see at the bottom. And what basically we have to find some balance between how much sound we want in the bright zone and how much sound we can cancel in the dark zone. And this is done by minimizing this objective function over the filter weight W. And we can see that apart from this balance between the first term, which has the part of the bright zone, so the part of the secondary sources, the sample of the secondary source is projected on the bright zone, and then the second term is how much of the sum of the sample created of the secondary sources HD times the filter weights added to the actual sample that the primary sources is created into dark zone, how much is still left, and then some regularization term just to tame the filter so there's no overfitting or whatsoever problem that we can find in this kind of inverse problems, right? Yeah. Well, once let's say the sample control technique or approach is defined, we have to also think about, okay, what could we do such that we can reduce the amount of measurements that we need in each of these zones, such that the application of such a system is feasible. And what we thought is, okay, can we have some kind of propagation model that, given a handful of measurements in each of the zones, we can fit this model with this measurement and then back propagate with simulation what's going on those zones. And this would be like estimated transfer functions that the sample controller will use to calculate the coefficients of the filter weights to have the optimal filters of the secondary sources. And that's basically this right now, this diagram is the full picture, you could say, of what we thought it could be a good solution for that problem. And just I would like to also explain a little bit what we see at the top is actual as a panoramic view of one concept that we had to go to try the system, which is a Kappa Future Festival in Torino. And I mean, we're talking here about, if I recall correctly, around 200, 300 meters, right? So to the very left, we have the concert venue, which you have people, basically. And to the very right, you have our subwoofer system, line array. And then even more to the right, there is a church, and we have to cancel the sound on that church. So it's a massive problem, I would say, in terms of deployment of equipment and also scale. Yeah. So the sound propagation model consists of two main parts, which is, okay, how can we model the sources in case that they are like way far from optimal monopole sources, you could say, and also how the medium can be modeled as well, right? So how the sound is propagated through the medium once the sources are well modeled. The first part of the source radiation modeling is based on spherical harmonics. They're widely, I would say, widely used and in let's say directivity modeling of sources. And the nice thing with the spherical harmonics is that it is quite you need a few parameters, not many, to actually have a good fitting of standard sources, you could say. So here what we can see is, okay, to the left we have a couple of modes of the spherical harmonics, the first two, monopole and dipole in certain axes, and then to the right we can see how each of these modes is activated for each function, for each frequency, once we fit a directivity of a source. So this is, for example, the case of, you can see the paper at the bottom, but it was in an anechoic chamber, and we had a scale model of what we could find afterwards in this Kappa Future Festival, for example. And we can see is that at higher frequencies, we will need more and higher order of this polynomial of spherical harmonics to account for the directivity of the sources. And to the very right, that's where we see the actual directivity fitted of this model of the source. So at 1000 hertz is quite more directive than at 100 hertz. And these results, they will scale more or less like 1 to 10 compared to what we see afterwards with subwoofers and sizes of the subwoofers and all that. So let's say that we need this model to fit these sources, because up to 100 Hertz, we have already directivity if we think 1 to 10. Yes. And then the next one would be the propagating medium. And what we did was very simple. Say, okay, can we just have some parameter in the wave number? So inside the Hankel function, HM2, then we have this K, and then we have tau. And tau will account for basically different speed of sound for different frequencies. It's quite, you could say, kind of naive, but at the same time, we didn't want to have like an overcomplicated problem because, sorry, a model, because it was already quite complex to make such a model to fit in such situation to something meaningful. And at the bottom, what we see is the relationship between all the variables of the problem in a Bayesian framework. And yeah, I mean, you can find more details on how the different parameters of the model are set, but we just found that Bayesian is very nice to set priors over your different parameters. And let's say that in such problems, we thought that having prior information was very valuable to try to scale down the model as much as possible. Yes. Yeah, and then I will just leave it to Franz and how all these, let's say, methods could. What was the performance of these methods in actual scenarios?
Thanks, Diego. So so I'm going to talk about all the experiments that we made, and this is just an overview saying that we did a lot of experiments. So some experiments in an alcoholic lab, but also on Resthallen, and we worked together with Tivoli and tried to set their Friedrichsrock concert series. And then we have some experiments on the Roskilde Festival side and also at this Kappafutte Festival. So in all of these experiments, we had like a similar setup like we've seen before. We have some concert loudspeakers, and then we have an audience area behind them or in front of them. And then behind the audience area, we have our control loudspeakers, and the controller speakers receive a filtered reference signal in such a way that they reduce the impact onto that they reduce the sound in the control area while reducing the impact on the audience area. And at the very beginning, we used the double layer arrays, as you can see maybe here and also up top here. And then in later experiments, we started to use cardioid subwoofers, so that just made it easier for us to focus on the control area and not so much on the audience area. So in one of these experiments that you can see here, this is on Roskilde. This was one of our more involved experiments. Here we can see a little bit the size of these experiments. So we have around 70 meters away from the primary loudspeaker, so from the concert loudspeakers, let's say, we have a control zone, which is 20 times 20 meters wide. And then we also have another zone further away at 130 meters. And what we would do in these experiments is that we scan the sound field with 10 microphones in each zone, and then do 10 measurements. So we move them 10 times. And we have to measure transfer functions from all loudspeakers. So you can imagine this takes quite a long time. So instead, what we also investigated is if we just select a random sample of these microphone positions and only measure, for example, at these 3 positions and then fit the sound propagation model, can we use the sound propagation model to estimate transfer functions at all these points and then use them for control. And down here, you see then the result of doing this. So here you see the insertion loss. So the amount that the sound pressure level was reduced on average in these 2 zones. So zone 1 is here and zone 2 is here. And we can see that we're working in the low frequencies. That's one thing. So we work only with subwoofers here. And we can also see that we actually can get really nice results, so up to 20 dBs in this low frequency region. But the most important thing is that, like, only using a few microphones, we can get similar results to when we have a lot of microphones. And then we can see that we can use this kind of approach also for doing control that's a little bit further away. So here we are 130 meters away, and we get similar results. So now I have a little video, and let's try if this one works. If you guys have headphones, it makes a lot of sense to put on the headphones because now we only hear bass. And I'll try to play this and see if this goes. Let me quickly see if I have sound on. Can you hear the sound?
Nope.
Nope. All right. And that was, of course. Of course, I forgot this time to set the checkbox.
No worries. Right.
So let's try this again. I hope maybe people found their headphones. All right. So so this is Diego walking through the first. So I think the most interesting thing is that now you can hear the serenity of the scene and the birds and people walking and strolling around. So maybe that was a little bit of an impression of what you can expect in such an experiment. So obviously there are some limitations of using the approach from us. One is that the sound propagation model only accounts for direct sound. So for example, here we see the sound field in this first zone at a single frequency from a single source. And you can clearly see that there's some refraction coming here from the side. So in this experiment, we had a big truck standing on the side with all the equipment, or that was transport all the equipment. And in the model prediction, we only have the spherical harmonics model. There's no reflection models. So this is one of the first limitations, and you can see the same thing here in the impulse response, where of course this reflection comes after, cannot be modeled. But another one is that we are also outside, and both wind and temperature can change, so we don't really have a time invariant system. So to investigate the effects of such changes in practice, we measured the sound field and computed our control filters in a certain condition. So this one you can see here. So you can see the wind speeds during this measurement took about an hour to measure. So it's about 2 meters per second, and the wind changed a little bit. And here on the right side, you can see the temperature, and then we evaluated the sound system at 2 other days using the same filters, where we have at 3 other days where we have some other conditions. And here you can see the impact on the insertion loss. So at here at day 1, we actually had very similar wind conditions, and we got really nice results. But then at the other 2 days, there was no wind, and the temperature was also slightly different. And you can see that insertion loss drops dramatically. So and this is not, it didn't rain or something like this. It was just normal summer days on Roskilde Festival, more or less. So now when we go to Rio Festival, where we tried these systems as well, obviously we have both issues, and both of them are quite prominent. So now we also have a picture of the scale here. So over there, we have our concert loudspeaker system, which is this little dot. And then 170 meters away, we have our 20 subwoofers in a nice line. And then we had this 20 times 20 meters control zone over here. And so in practice, what you do when you go to a festival, you have a sound check, and you get maybe an hour to play the loudest sweeps that Torino has ever heard, and tune your system, and that's more or less what you can do. And then you look at what the result is during the 2-3 day festival. So in here you can see insertion loss, average insertion loss in this control zone. And we see two lines. So one is what we estimated, and then what we measured. And so the estimation is actually not too bad, but it's also not really good. So this is around 8 decibels. And this is of course, because here we have many reflections that we can't really reproduce with our sound propagation model, or even many reflections that we can't reproduce with our control sources. So to cancel sound effectively, we have to more or less create the same sound, but from a different location. And if we have a challenging environment like this is obviously very complicated. But then we also see that when we measure, we get an even lower reduction. This is also that here the temperature changes quite a lot. This is San Marino. During the day, it's like 35 degrees, and in the evening, it gets around 18 degrees Celsius. So in our PhDs, we also investigated then weather influence. And if we could find simple models to model this impact on sound propagation. So we had an experiment, a 5-day experiment in Riese. So there DTU has like a wind park, and the useful thing is that we have like a big weather mast here, and we measured transfer functions of around 300 meters between 2 loudspeakers and a big weather mast in the middle, where we could measure wind and relative humidity and temperature, and then find simple models that explain the variation in sound propagation given weather data. And our idea was that if we have a measurement of a single reference transfer function, can we find this simple model of just a delay and a constant gain that then will model the actual measure transfer function. And the idea was to find this delay and gain just from weather data. So, and here we see such a model that from the effective wind speed, so that's the wind speed, so sorry, the effective speed of sound, so that's the effective wind speed, so that's the wind speed in direction of sound propagation, and from temperature at some height on the weather mast, we can estimate with a linear model more or less the time delay that is introduced by the weather variations. And a similar model can be found for the gain. And then we get results like this. So here you can see the measurements over these 50 days. Over these 5 days, around 80 measurements, and we can see the temperature changes and the wind changes. And here on the right, we can see the insertion loss that we get during our measurement session. And if we have just a constant filter with this reference transfer functions, then we can see that the insertion loss changes quite drastically over these different weather situations. But then if we have weather data and we can estimate the time delay and gain, we can recover actually at least some amount of insertion loss. Yes. So I want to conclude. We looked at large-scale reduction of sound from outdoor concerts, and we've seen that this is possible, and especially on flat terrain and with constant weather conditions. So flat terrain, because then the sound fields are simple and we can reproduce the same sound field from another position. And constant weather conditions, well, because those change the transfer functions over time. We've seen that there's a large measurement effort, and this one can be reduced by fitting a sound propagation model to just few microphone positions. And also this is especially applicable if you have a flat terrain where there's not many reflections, or you're in highly damped spaces like an anechoic chamber, for example. And we've also seen that the weather influence is quite important, and especially that one can find simple models that, given weather measurements, can account for some of these variations in transfer functions. So going back, so this is Kapafute Festival, and I hope maybe you guys got a glimpse of what one could do in practice to reduce sound actively at such events. So thanks for your listening.
Thanks, guys. Wonderful. I all I can think about, oh my God, so much work, all those speakers, like I can only imagine.
Yeah.
Oh my God.
There was that, yeah.
Okay, can you stop sharing the screen and then we can put this in gallery view? Okay, I think we're in gallery view already. So yeah, perfect. So much knowledge all in 1.5 hours. So let's see what people are asking. And of course, I mean, we don't have a lot of time left, but I guess if it's okay, we can also exceed the time a little bit if you have some extra minutes. If you have to go, you're also welcome to. So I will just start here with Michael Wiertzfeld's question. Ming, you mentioned the use of an LMS adaptive filter to model the feedback back to offset feedback. Are there other types of adaptive algorithms that have been used? You have to unmute first, sorry.
Thanks. Thanks for the question, Michael. I mean, it's a very good question. I mean, I can of course not know, you know, all the methods that others, you know, whoever might have used. But as also Professor Doctor mentioned that, I mean, it's maybe not reported in the literature, but typically when you have feedback path changes, that a very simple LMS algorithm works many times as the best. So I think, I mean, yes, I mean, they are. I'm pretty much aware of that. There are more advanced algorithms that people also have proposed in the literature, that you can make use. I mean, even I have seen publications with using Kalman filter for feedback cancellation. Of course, then complexity, you can say complexity is a maybe an issue for hearing rate. But I would say for the quick change of the acoustic feedback path, a simple algorithm like LMS is not a bad choice, because I mean, this is a little bit linked to the, you can say for LMS, the simple one, there's no memory in that. You just take the latest input, the error signal, reference signal. But if you take the more advanced algorithm, if everything is stationary, and then you want just to get to the right estimate, it can, and you have all the data available, maybe in an offline manner, then you can reach to the minimum rather quickly than LMS. But as you have to do this like online processing, like symbol by symbol based processing, actually LMS kind of algorithm is actually quite good choice. So I don't know if this answers your question, but
does anyone want to add something to? No. All right, perfect. Ming, so then a second question, follow up, can you share any references for the STM method?
Sure, I will do that, yes.
Okay, then we can include it in the follow-up email. We can do that. I'll ask you via email.
Sure, thanks.
Perfect. Then we have Lila Krishna. She said, can we assume that the largest possible delay is fixed based on the design of the hearing aids? Or how do you decide how long the adaptive filter should be? I don't know. I guess this could be both for Ming and Simon. So go ahead, guys. Whoever wants to. Maybe Simon can go first.
Yeah, but I would have to ask what is the question really, because there seems to be two questions. What is the largest possible delay between what I would ask, and how long the adaptive filter is? I mean, yeah, it of course depends on the distances between the loudspeaker and the microphone. So typically in hearing aids, you could use rather short adaptive filters, I would say. Of course, for other applications in large rooms or something, we didn't talk about it. But if you want to control feedback there, then of course you need much longer filters. But it's basically these distances that determine these lengths of the adaptive filter. Regarding delay, I'm not sure what is exactly meant. If it means delay in the adaptive filter or the processing.
Yeah, she said possible delays fixed based on the design of the hearing aid? So
I'm not designing hearing aids, so I leave that question to Meng.
yeah, Meng, if you can complete, that would be
Sure.
great.
Thanks, Simon. I mean, I read this question as the possible delays, maybe the latency or from the input to the output, and if that is fixed based on the design.
Yeah. So how do you decide how long the adaptive filter should be?
Yeah, I mean, if it's the latency of the hearing aid, typically I would say it's quite fixed. I mean, you can of course, I mean, whenever you are in a certain program, you cannot just change the delay in your hearing aid. I mean, because then you will change. I mean, you will have a glitch in your sound, typically. But you can have a different programs, and you can have a different delays. I mean, this can happen. But typically, then how long the adaptive filter should be. This is actually I mean, this is a little bit independent to the latency of the input output latency, because as also Simon mentioned, that this is more related to the length of the acoustic transfer function, or the impulse response of the acoustic transfer function. So if you are in a hearing aid application, as the distance is very short, you can actually have a relatively short filter. So it's like typically I would say a few milliseconds you have to cover. But of course, if you're getting, then you can go to a critical acoustic situation. If you're getting close to a wall, then the distance getting longer, you might need a bit longer filter. So, but it's still in the shorter end. But if you have to deal with the feedback problem in a room, then is the room, you can say the impulse response, you have to be able to cover with your filter. So in that case, it has to be much longer. So that depends on the application, I would say. Yeah, but typically for a hearing aid, the distance is short. It's maybe just a few milliseconds will be enough.
Yes. Okay, perfect. All right, then we have Jakob Brink here, but he wrote Professor Simon, but he didn't write a question. So if Jakob, if you want to write again, please do. And then we have Daniel Says, I don't know how to spell it. A question about latency. Only the sound control presentation accounts for delay. How important is variable delay for the stability of the other methods? I'm not sure. Do you guys follow this? I think it's for friends, maybe, or it's in the chat. Question about latency. Only the sound control presentation accounts for delay. He wants to know the impact of variable delay. I would guess this is about the last presentation. Daniel, if you can write a bit more. But are you thinking about something, friends?
I guess the impact of variable delay is in regards to the weather impact and these little weather models. But I can't really actually see that question here. It doesn't show up.
No, it's in the chat actually. But if the delay in the chain is variable, does the model still work?
Yeah, I mean, one can update the transfer functions accordingly, and the sound propagation model could also use that information. I think, like if then one had an adaptive system, which we didn't really look into, then I think this would be quite straightforward.
Cool. Diego, do you have something to no? You're good? You agree with your colleague?
Yes, exactly.
All right, cool. All right, then meanwhile, Stefan Liebich wrote a few questions here for Professor Doklo, and the first one is, would you say your device with balanced armature drivers are well suited for the integration of ANC? Did you investigate stability in terms of variation of fit?
Okay, thanks. The name is Stefan Liebich. Thanks, Stefan. So on the first question with the balanced armature drivers, I cannot really comment. I don't have any good answer. I mean, because we just used the loudspeakers that were in the device. The second one, stability and variation of fit. Yes, of course. So actually, I would say there's two procedures that we follow there. Either we have measurements, we have multiple measurements for different variations of fit for different reinsertions for different persons, and then we design actually the filters such that they are all taking into account these measurements, and they're stable and they're performing well for all of these fits. Secondly, it's also possible, although we haven't really completely finished this research, to also use these individual electroacoustic models. I did not really talk about this in my presentation, but there's also methods that use the device and then estimate actually from the inner microphone the ear canal model, and then also the transfer function from the loudspeakers to the eardrum. Of course, it's not perfect. There's variations there. There's some modeling errors there, but that's also what we then use in the design. But variation of fit is always very important, both individualized as well as the reinsertions. I hope that's what your question was about.
And then there's a follow-up question. Could you comment on where you see the major challenges with the occlusion effect and finding a good active solution for it?
Yeah, occlusion effect, I did not completely talk or not really touch upon this. Although I would say with feedback, active feedback cancelers, they're actually quite good both for active noise as well as for active occlusion. All the sounds are there. If it comes from external or internal, it can be cancelled. And I would think actually, I know Stefan that he also has solutions for that are maybe even better than what we have. What we're still working on, that's maybe what I would like to comment, is that we think that for occlusion effect, that's when, of course, you have your own voice, that you could also really make these filters dependent on the speech itself, which is being spoken, because these transfer functions are quite dependent on for example, the phonemes. We did some initial measurements there, and we saw that there are really phoneme-dependent transfer functions or transfer characteristics. We would like to exploit them. But that's work in progress.
Perfect. And Stefan says, yes, it's a good answer. And thank you.
That's good. I'm happy.
So Lila Krishna, she's asking to Friends and Diego, how do you choose your era mic position in such large areas?
Can you hear me?
Yes.
Yes. To be honest, we didn't. I mean, we thought is okay, as long as they're not too close together, then we get the most information as possible from the sound field. But we never. This is something we had in mind to have like research on how is this basically get the most information out of the measurements. Like you have a model and then you have some variability of the predictions, and those measurements that they're going to reduce. Yeah, they give you most information basically of according to that model. But that was just something that we thought we never did, and in the end it was okay. Can we just take randomly something that is not too close to each other? And that's it. Yeah. But there are ways, and you can use, I don't know, Gaussian processes or stuff like that, where you have something that accounts for the variability of your model, and then you want to place a measurement where you know that the highest variability is going to be addressed. So it just you close that gap somehow.
Friends, you want to add something? Or?
No, I would maybe the only thing I can add is if Lila, if you're interested in optimal sensor placement, then there's some work here at DTU from Samuel that he works on optimal sensor placement right now and has some really interesting work on that. So I would refer you to him and maybe look up his papers. Samuel, I'm not so good with the last name.
All right. Okay. I have one more question from Leila. So if you want to increase the quiet zone, you just increase the distance between the mics?
So I would say to this that in principle, yes, but then it depends really on your geometry of where you have sources, how big you can actually make this quiet zone, because at some point you will make it so big that your control sources, they will not be able to synthesize a sufficiently accurate sound field such that it actually cancels over such a big area. So that has to be taken into account as well. Thanks for the question.
Cool. All right, there's one more, and then we'll close it because we're way over time now. And this one goes for Meng. Can it, because it's a rephrase from Daniel's question, can a change in the delay be considered? Can a change in the delay be considered a change of feedback path? Does it change the compensation efficiency? Do you understand that, Meng? Yeah. Yes.
Okay, I might have an idea. Let me see.
It's in the chat, actually. It's not in the Q&A.
Okay, yeah. Well, I mean, I assume that this delay that we are talking about is the delay in between is the hearing aid processing delay. So it's like something you are in control of. If you change that, depends on if this delay is in your you can say estimation loop. If it's done, I mean, if you change this delay in principle, this is something you are in control of. You know of that. So therefore, you can compensate. You can always compensate for that. So saying that if you add more delay to your forward path, even the forward path is part of your estimation loop, you can take care of that. So I would say this should not have a negative effect on your performance.
Mm-hmm. Great. All right, guys. Thanks a lot for all the sharing, all the beautiful information and sharing with the community. It's a pleasure to have you here. Thanks a lot. And that's it. See you around. Thank you for coming.
Thank you.
Thanks. Bye-bye.
Bye-bye.
Bye. Bye.
Bye.